We now discuss how to use a graph approach to solve for an LP model. As we know, the constraints of the LP model define the feasible area of the entire problem. And if we can find the best point in the feasible area, and that would be the optimal solution. For an LP model with two distinct variables, it's easier to plot all the constraints on a graph to define the feasible area such that we can find the optimal solution. For example, coming back to the Blue Ridge case, we have the objective maximizing 350x1 plus 300x2 subject to the constraints of x1 plus x2 less or equal to 100, 9x1 plus 6x2 less or equal 1566, and 12x1 plus 16x2 less or equal 2880. We also have the two non-negative constraints, x1 and x2 larger or equal 0. In order to use the graph approach to solve for the LP model, we need to have two dimensions. One we call x1 for the horizontal line, and we have x2 for the vertical line. Before we draw all the constraints on the graph, we need to first determine what range is enough for x1 and what range is enough for x2. In this case, if we go back to the LP model and we look at the right-hand side value, the 200 for pumps, 1566 for label, and 2880 for the tubing, and the left-hand side equation, we kind of determine that the value of the 250 might be enough for us for the x1, and 250 will be sufficient for x2 as well. So that will be the two values we decide for the horizontal and vertical lines. Now we can put the first constraint. The first constraint is for the pump. We have x1 plus x2 equal 200. Right now we just care about the equal. We don't have to put the less or equal right down in order to draw the line. So we have 2 points to draw a line. In this case, we can have x1 equal to 0, and in order to have the equation satisfied, we have x2 equal to 200. So we have the first point, x1 equal to 0 and x2 equal to 200. If we set x2 to 0, we have 200 for x1. Right now we have 2 points. We connect those 2 points, we have the first constraint line. And the left-hand side of the constraints would be the feasible area for these specific constraints. Now let's look at the second constraint. We have the 9x1 plus 6x2 less or equal 1566. Of course, right now we just need to look at the equal line. So we have 9x1 plus 6x2 equal 1566. If we put x1 equal to 0, we have x2 equal to 261. If we set x2 to 0, we have x1 to 174. And we have 2 points right now in order to draw a line. So we put the second constraint on the graph. And the left-hand side of this constraint will be the feasible area of this constraint. Similarly, we have the third constraint, 12x1 plus 16x2 less or equal 2880. Again, we just need to care about the equal sign. So let's set x1 equal to 0. So we have x2 equal to 180. If we put x2 equal to 0, we have x1 equal to 240. So with those 2 points, we can draw the third constraint on the graph. Right now, we have all the 3 constraints plotted together with the 2 non-negative constraints defined by the axis of x1 and axis of x2. We have the common feasible area for the entire problem as highlighted in the blue. And let's take a closer look at the entire feasible area. Right now, actually, we have 4 corner points of the entire feasible area. We have the top one will be 0, 180, and 80, 120, 122, and 78, and 174, and 0. We also have 0, 0 point. All these 5 points, we call them as extreme points. Extreme points actually are the corner points of the feasible area. There's one very nice feature of the linear programming is the optimal solution must happen at least one of the extreme points. So because of this feature, we can solve linear programming in polynomial time. It means we can relatively solve this problem quickly compared to other nonlinear programming. So there's one approach for us to solve for the optimal solution. Given that we know the optimal solution must happen at one of these extreme points, we just need to put those 5 points into the objective function, and we get the optimal value. For the point of 0, 180, we get 54,000. For the point of the 80, 120, we get 64,000. For the point of the 122 and 78, we get a value of 66,100. For the point 174 and 0, we get the value of 60,900. Of course, for the 0, 0 point, we get the 0 for the optimal value. Compare all these objective values, we can identify that the point of 122, 78 will give us the highest objective function value of 66,100. So this point will be the optimal solution point for us. But so far, actually, we have not utilized the objective function line. We just use the feature of the linear programming and enumerate on every potential extreme points and figure out which point is the optimal solution. If we want to utilize the objective function, we can actually draw a level line for the objective function. And we take on the objective function 350x1 plus 300x2. We are going to assign an arbitrary value to this equation so that we can draw a line, we call level line, on the graph. So in order to draw the line on the graph, let's set the 350x1 plus 300x2 equal to 350 times 100. So we have 35,000 for the right-hand side value. We can draw the line, we call the level line on the graph, so that we have a line with 2 points. One is 0, 116.67, another point is 100, 0, and we have the objective function line. You might argue that this line is too far away from the boundary, so we can definitely have the second objective function level line. For example, if we set the right-hand side value of the objective function, we have 350 x1 plus 300 x2 will be equal to 52,500. We can again draw the level line on the graph. We can right now use a ruler to move in parallel to touch the last point of the feasible area. Recording that we have a maximization problem. So we try to touch the last point outside, going up the last point of the feasible area. And in this case, we can identify that the point of the 122 and 78 will be the optimal solution point. As long as you can move your ruler comfortably to touch only one point of the corner points, and you can identify the optimal solution. But if your graph is not perfect and it will be difficult for you to identify the optimal solution point, you might still go back to enumeration, try to compare those two close points and figure out which point will give you a higher value of the objective function. In this case, we can identify that the optimal solution will be given by two constraints. And these two constraints, we call them binding constraints. And we know that if we go back to the model, we have the first binding constraint will be defined by the palms constraint. The second constraint will be defined by the labor constraints. Now we need to solve for this optimal solution point out of those two binding constraints. Let's come back to the binding constraints computation. We know that the palms and the labor constraint would define the optimal solution. So we rewrite those two constraints over here, x1 plus x2 equal to 200, and 9x1 plus 6x2 equal to 1566. In order to solve for the optimal solution, we need to move one of the decision variable to the other side. So in this case, we can plug in the new equation 3, x2 equal to 200 minus x1 into the equation 2 of the label 9x1 plus 6x2 equal to 1566. So we have 9x1 plus 6 times parenthesis 200 minus x1 parenthesis it will equal to 1566. And we can solve for x1, that will be equal to 122. Right now, we can plug in x1 equal to 122 back into the equation 1. So we can have x2 equal to 200 minus x1 equal to 78. So we get the optimal solution, x1 equal to 122 and x2 equal to 78. We plug in these two values into the total profit function, and we have the 350 times 122 plus 300 times 78 equal to 66,100. Just now, we solved for a problem with maximization objective. In that case, we try to move the level line of the objective function outwards to touch the last point of the feasible area. Right now, suppose we have a minimization problem. This is another case, but suppose we have the feasible area as defined in the blue dotted line. Right now, because we have a minimization objective, we are not going to move the level line outside. Instead, we want to move the level line inside to touch the last point of the feasible area. That will be the last feasible point inward of the feasible area. So in this case, this point will be the optimal solution point. Thank you.